Have you ever wondered what physics is being used that enables an airplane to fly? What it all comes down to is the use of the properties of Bernoulli's principle. By properly using Bernoulli's principle, that enables a 250-foot long, 212-foot wide, 776,000 pound airplane that is carrying 400 passengers to fly 6 miles in the air to a destination halfway across the world.
The Bernoulli principle relies on the Bernoulli equation. The Bernoulli equation can be considered to be the statement of the conservation of energy principle appropriate for flowing fluids. As seen in the airplane example earlier, the qualitative behavior behind the Bernoulli principle is usually labeled with the term the Bernoulli effect, which is a lowering of fluid pressure or air in regions where the flow velocity is increased. So the top side of the wing versus the bottom side of the wing will create a lift, as we'll talk about later. But Bernoulli's equation is essentially the energy per unit volume before is equal to the energy per unit volume after. This is depicted with the formula P1, which this here will represent your pressure energy, plus 1/2 rho and velocity 1 squared, which this section here is equal to, or it represents the kinetic energy per unit volume. And so you take that, so you have your pressure energy plus your kinetic energy per unit volume plus rho g for gravity and your height, which represents the potential energy per unit volume. So you have your pressure energy plus your kinetic energy per unit volume plus the potential energy per unit volume is equal to it'll be the same thing, but instead of P1s it'll be P2, instead of V1 it'll be V2, and H1 will be H2. And that satisfies the idea that the energy per unit volume before is equal to the energy per unit volume after. A good way to depict this would be in your classic Bernoulli example of a pipe with the constricted area. You make the assumption that this is a laminar flow. The assumption is going to be made too that A2, which is this area, will be less than A1, which would be this area. So A1 would be your radius here, A2 is going to be that area there, and V2 is going to be greater than V1. V2 is going to be in the constricted area here next to V1, or next to A2. V1 is going to be out here. And the representation of the fluid going through would be like so. So as you can see, it gets constricted in that area, so the velocity is going to increase. Depicted earlier, and with the airplanes taking off and landing, the Bernoulli principle was demonstrated. The reason why that works the way it works is the air, as it hits the wing, or this is when the plane is landed and stationary, and as the plane's taken off, if this is the wing, it's going to tip to be at a greater angle. And so your air, as it's coming across the top of the wing, relative to the wing itself, is going to be going at a higher velocity, which creates so you'll have your wind speed, your air coming in, and when the wing is flat, the air will move around the wing easily without causing any sort of lift. But then as you have the wing a lot more tilted, it'll the wind has to travel on the bottom. It won't have to travel as far as it does at the top, and so this airspeed, the velocity increases quite a bit, which will create a little bit of eddies and turbulence behind you, but also create a low pressure zone, which will create lift in the wing. And this happens because the wing gives the air a downward force according to Newton's third law, and the wing experiences the opposite effect, which will create a lift. As noted earlier when it was landing, when the wing comes back down, it doesn't return just to this state. It has little wings, it has little things that come up and down that essentially are causing the wing to theoretically the wing is going to just go flat, because then there's going to be too much. The wind is going to hit this and it's going to be a buffer, and rather than creating a lift like before, it's going to increase the drag to a high enough force where it'll stop the airplane.
Example of Bernoulli's equation that can be done at home can be done with the use of a few balloons and some string. What you do is you blow the balloons up, then put them onto a string, and then tie the strings up to a ruler so that when the balloons are free hanging, they're about 5 inches apart from each other. Then, by blowing quick air between the balloons, it should cause the balloons to pull together, like so. The reason that occurred is because of the Bernoulli principle of the high-speed air between the two balloons causing low pressure between the balloons, which makes the static air push the balloons together, making the balloons appear to stick together due to the high air between it.
Alright, today we're going to show you a quick, easy example of how to use the Bernoulli equation. It's going to be a tank with the fluid water inside of it. So the tank is going to be here. There's going to be a little spout at the bottom, towards the bottom. It's going to be subject to the atmosphere. So this is H2O, and the fluid will be coming out right here. We're looking for the velocity. We are also given the height, which is 2.4 meters. And so we have to pick 2 points here. Our first point is going to be at the top, right there. Our second point is going to be down here, right where the water comes out. So that's point 2. This is our reference height. And so we will start by using the Bernoulli's equation, which is P1 plus rho GH1 plus 1/2 rho V1 squared is equal to P2 plus rho GH2 plus 1/2 rho V2 squared. P1 is subject to the atmosphere, so that will be PATM plus rho GH1, which is going to be 2.4 in the end, plus 1/2 rho V1 is going to be equal to 0, relatively equal to 0, because it's going to be moving so slow relative to the way that it's coming out of the spout. So we consider that equal to 0. So this whole term is going to be equal to 0. That is all equal to P2 is subject to the atmosphere at this point as well. So that's PATM plus rho GH2 is considered to be equal to 0 here. This is our reference height. We're just measuring using the pressure differences here from 1 to 2. So the height just goes from 2.4 to this 0 value. So H2 is going to be equal to 0. So that whole thing will go to 0. Plus 1/2 0. Plus 1/2 rho V2 squared. That's the term that we're trying to find. Okay. So the atmospheric pressures will cancel out as well. So we'll be left with rho GH1 is equal to 1/2 rho V2 squared. We will multiply both sides by 2, and these will cancel out. So we will be left with 2 GH1 is equal to V2 squared. So we will take the square root of each side to get rid of the square terms. V2 will be equal to the square root of 2GH1. We know gravity, we know the height is 2.4, and so V2 is going to be equal to the square root of 2 times 9.81 meters per second squared, multiplied by H1, which is 2.4 meters. So V2, all that calculated, V2 will be 6.86 meters per second.
Bernoulli's principle can be observed at home by the use of a ping pong ball and a string. What you do is hook a string up to the ping pong ball and you set it next to the faucet of water, or a faucet, and you swing the ball like that. Once you turn the faucet on, the faucet will suck into the ball and hold the ball at an angle position. The string can't be seen, but it's actually sitting at an angle there, and it should have pulled away, but due to the force of the water, it's holding the ball off to the side. The reason that occurs is because the fast-moving water flowing alongside the ball is creating low pressure on this side, which then when the ball gets sucked into there, the low pressure holds the ball at an angle. This can be done at home.